Hi, I'm Anna Savage, a physical oceanographer at Scripps Institution of Oceanography in San Diego, California. My research interests are in internal waves, which are a lot like surface waves but propagate at the interfaces of density layers within the ocean. Surface waves, like we see at the beach, are usually a few meters tall but have short periods of less than an hour. Conversely, due to the low density differences in the ocean, internal waves propagate very slowly and can have periods longer than a day. But sometimes their amplitudes can be hundreds of meters tall, and when these waves break, they dissipate all of that energy and mix the ocean. This mixing has important implications for marine ecosystems, since breaking internal waves can mix temperature, salinity, and nutrients vertically in the water column. Even though these internal wave amplitudes in the ocean interior are huge, internal waves have sea surface height signatures that are only a few centimeters. This makes them very difficult to observe globally with current observational tools like satellite altimetry. Making global observation even harder, internal waves can interact with other ocean dynamics, which can change their propagation patterns. Similar to how surface waves can wrap around points on the beach, changing their propagation direction, internal waves can interact with ocean dynamics such as eddies and fronts and also get redirected or altered. These interactions are also usually accompanied by an energy exchange between the internal wave and the background feature. This energy exchange and the altering effects of the background dynamics on the internal waves is the primary focus of my research. The two primary sources of internal wave energy are tides and wind. Internal waves generated by tides, or internal tides, have large input signals around bathymetric features where internal tides are generated. Internal waves generated by wind, or near inertial waves, have large input signals in high latitude regions where storms are severe and thus wind energy input is large. While we know a good deal, although still not everything, about how internal waves are generated, a big open question is this. What is the fate of all of the tide and wind energy that is input into the internal wave field? This question can be broken down into three sub-questions. 1. How far do internal waves travel? 2. How much energy do internal waves give and take from low-frequency background dynamics? And 3. How do internal waves contribute to mixing? Or more specifically, what sets the conditions for internal wave breaking? To address these three questions, I use both numerical and observational techniques. I have used global ocean models to estimate the centimeter scale surface height variance associated with internal waves of different frequencies. I have also used a small simplified physics model to quantify some of the altering effects that a background flow can have on internal tides generated off of the southern tip of New Zealand. Both global ocean models and simplified physics regional models can provide beautiful maps of internal waves around the world. They also provide invaluable context for in situ observations. To gather real-world data, we use a multitude of instrumentation that spans all scales of oceanographic dynamics, from basin scale dynamics like western boundary currents to the dissipative scales of about a centimeter. Gathering these data can be a daunting effort, and the ocean can often be an inhospitable place for fieldwork, particularly when you are interested in wind-driven circulation, like I am. But in the end, the in situ data collected from fieldwork not only provides incredible snapshots into the intricate dynamics of the ocean, they also provide necessary information used in parameterizing climate models and guiding their development. In summary, even though internal waves are relatively small scale in the grand scheme of our global oceans, the role they play in ocean mixing and ocean energy dissipation is an important one. Understanding internal wave propagation and energy loss is a necessary step in quantifying these roles and describing global ocean energy distribution.